Imagine holding in your hand a device no larger than a fingernail, yet within its slender boundaries hums the collective power to guide rockets, animate smartphones, and fuel the digital world. This is the microchip, sometimes called an integrated circuit, a marvel of modern engineering that quietly orchestrates the operations of nearly every electronic device we rely on today. To appreciate the microchip's significance, it helps to understand not only its intricate structure and purpose, but also how it emerged from the aspirations and ingenuity of 20th century scientists. The story of the microchip begins with the challenge of miniaturization. In the early days of electronics, circuits were made from bulky, discrete components, vacuum tubes, resistors, capacitors, and miles of tangled wiring. These early inventions powered radios and the first computers, but their size and fragility posed severe limitations. As devices became more ambitious, engineers faced a fundamental question: how could they make circuits smaller, faster, and more reliable? A breakthrough arrived in 1947 at Bell Labs with the invention of the transistor, a tiny electronic switch made from semiconductor materials. Transistors quickly proved superior to vacuum tubes. They were smaller, consumed less power, and were far more durable. This new device was fashioned from semiconductors, substances like silicon whose ability to conduct electricity could be carefully controlled. The unique properties of semiconductors made it possible to build components that could either block or permit the flow of electric current, depending on how they were treated and connected. Although transistors revolutionized electronics, assembling circuits still required physically wiring together each component by hand. This painstaking process limited how complex or compact a device could be. The next leap forward came from integrating many components, transistors, resistors, capacitors, onto a single piece of semiconductor material. In 1958, Jack Kilby at Texas Instruments demonstrated a working, integrated circuit. His prototype was simple, just a sliver of germanium with a handful of interconnected components, but it proved a profound concept. Entire circuits could be built as a unified structure rather than as an assembly of separate parts. Almost simultaneously, Robert Noyce at Fairchild Semiconductor developed his own version of the integrated circuit, using silicon and a process that allowed easier mass production. Both men are credited with inventing the microchip, and their work set the stage for the revolution in electronics that followed. At its core, a microchip is a wafer-thin slice of semiconductor, most commonly silicon. This silicon base is meticulously processed to form a complex network of microscopic components, primarily transistors, the fundamental building blocks of digital logic. A single microchip can contain millions or even billions of transistors, each acting as a tiny switch that controls the flow of electrical signals. By arranging these switches in various configurations, engineers create logic gates, the elemental units of digital computing. Logic gates perform simple operations, AND, OR, NOT, and by linking them together, they enable the sophisticated processing that defines modern computers. To understand why silicon is so vital, it's helpful to consider the nature of semiconductors. Unlike conductors, which allow electricity to flow freely, or insulators, which block it entirely, semiconductors occupy a middle ground. Their conductivity can be precisely manipulated by introducing small amounts of other elements, a process called doping. This ability to tailor electrical properties makes semiconductors ideal for creating the tiny, switch-like behavior required for transistors. Manufacturing a microchip begins with a flawless wafer of pure silicon. Through a series of chemical and photographic techniques, intricate patterns are etched onto its surface layer by layer. At each stage, regions of the silicon are transformed to form transistors, resistors, and capacitors, all interconnected by ultra-thin metal traces. The result is a densely packed circuit of astonishing complexity, all confined to a space smaller than a postage stamp. The advantages of microchips over earlier, discrete components are immense. Integrating all the elements of a circuit onto a single chip makes devices smaller, faster, and far more reliable. It also enables mass production, as the same process can be used to create thousands of identical circuits from a single silicon wafer. These benefits transform not only consumer electronics but also fields as diverse as aerospace, telecommunications, and medicine. The first applications of microchips were in military and aerospace systems, where saving space and reducing weight were critical. Early computers for spacecraft and missiles used microchips to pack sophisticated control systems into compact spaces. As manufacturing improved and costs fell, microchips found their way into commercial products. Calculators, hearing aids, and eventually personal computers became possible thanks to the relentless miniaturization and integration enabled by the microchip. Fundamental to this progress is a principle known as Moore's Law, named after Gordon Moore, co-founder of Intel. In 1965, Moore observed that the number of transistors on a chip tended to double approximately every 2 years, leading to exponential increases in computing power. While not a scientific law, this observation became a self-fulfilling prophecy, driving the industry to continually shrink components and pack more functionality into each new generation of chips. There are many types of microchips, each tailored to specific roles. Some, like microprocessors, are the brains of computers, handling calculations, logic, and control. Others, like memory chips, store information. Analog chips process signals that vary smoothly, such as audio or sensor data, while digital chips handle information in binary form, ones and zeros. Some microchips, called mixed-signal chips, combine analog and digital functions on the same device. Over time, engineers have developed highly specialized chips, application-specific integrated circuits, or ASICs, designed for particular tasks, and system-on-a-chip designs that integrate entire systems, including processors, memory, and interfaces, onto one silicon substrate. The microchip structure is multi-layered, both literally and figuratively. At the bottom lies the silicon wafer, carefully refined and sliced from cylinders of crystalline silicon. Above this, layers of circuitry are built up, each separated by insulating materials. Transistors are arranged by the millions or billions, their connections defined by micron-scale metal pathways. The complexity of these designs is staggering, yet each chip operates in silence, switching currents on and off at blinding speeds to process information. Underlying all of this is the science of semiconductor physics. The behavior of electrons in silicon, the way materials are doped to create regions of differing conductivity, and the interactions between electric fields and atomic structures, all form the foundation for how microchips work. Transistors, the heart of every chip, rely on these principles to act as switches or amplifiers, controlling the flow of charge with exquisite precision. By grouping transistors together, engineers realize logic gates, the building blocks of computation. These gates, in turn, are combined to form adders, registers, processors, and ultimately, the complex architectures that drive modern technology. The journey from bulky vacuum tubes to the sleek, nearly invisible microchips of today has been one of relentless innovation. Each advance, whether the invention of the transistor, the first integrated circuit, or the ongoing miniaturization of components, has enabled new possibilities, shrinking computers from room-sized behemoths to pocket-sized companions. The microchip is, in a real sense, the silent architect of the modern world, shaping the tools and systems that define contemporary life. As we look ahead, the microchip's influence only grows. New manufacturing techniques, novel materials, and ever-shrinking features continue to push the boundaries of what these tiny devices can achieve. Yet at their heart, microchips remain true to the principles first demonstrated by Kilby and Noyce, integrating vast complexity onto a single, elegant piece of silicon. Their story is one of imagination, precision, and the unending quest to master the invisible currents that power our lives. In the quiet hum of a modern computer or the subtle glow of a smartphone screen, billions of tiny components work together, orchestrating a symphony of zeros and ones that power our digital world. At the heart of this silent revolution lies the microchip, a marvel of engineering, both astonishingly complex and elegantly precise. To truly appreciate how microchips perform their magic, it helps to picture their operational mechanics, the process by which raw, lifeless sand is transformed into the living brain of silicon, and how these chips process information at lightning speed. The journey begins with silicon, which starts as humble grains of sand. This sand is refined and purified until only silicon remains, a painstaking process that removes even the tiniest traces of impurity. The result is a gleaming cylinder known as a silicon ingot, grown over days or weeks to achieve flawless crystal structure. These ingots are sliced into thin, mirror-like wafers, each one destined to become a canvas for intricate circuitry. The transformation from wafer to microchip is a dance of chemistry and light. First, a wafer is coated with a thin layer of material in a process called deposition. This layer might be conductive, insulating, or semiconducting depending on the stage. The wafer is then covered with a light-sensitive material called photoresist. Imagine a photographer exposing film, except here, a carefully designed pattern is projected onto the wafer using ultraviolet light. This is photolithography, a process that allows engineers to etch patterns with astonishing precision. Where light touches the photoresist, it changes chemically, so that when the wafer is washed, only selected regions remain covered. The exposed areas are then chemically etched away, carving out the shapes that will form the chip circuits. Layer upon layer, this process is repeated, depositing, exposing, etching, and cleaning, each time adding new levels of complexity. Some chips may require dozens or even hundreds of such layers, each aligned to the last with nanometer precision. What emerges from this process is a wafer studded with thousands of identical microchips. Each chip contains a maze of interconnected components, transistors, resistors, capacitors, and the ultra-thin metal lines that link them together. It is the sheer density of these elements, packed onto a surface smaller than a fingernail, that gives microchips their astonishing power. This density is made possible by miniaturization, the steady shrinking of features on the chip. In the early days of integrated circuits, the width of a single line etched onto silicon might have been measured in micrometers, a fraction of the width of a human hair. Today, the industry measures its progress in nanometers billionths of a meter, with milestones at 14, 7, and even 5 nanometers. Each new node, as these generations are called, represents a leap in the ability to pack more transistors into the same space. As features shrink, more complex and powerful circuits become possible, all while consuming less power and generating less heat. The challenge of making features this small is immense. At these scales, light itself becomes too blunt an instrument. Engineers must use advanced techniques, such as extreme ultraviolet lithography, to write the smallest patterns onto the wafer. New materials are constantly being explored to push the limits of miniaturization. For example, researchers have developed innovative metal organic compounds and advanced light beams to deposit materials at the atomic scale, crafting circuits that are not just smaller, but also more efficient and reliable. Inside each chip, billions of transistors are arranged into logical building blocks known as logic gates. Although the details of transistor and logic gate operation have been discussed previously, it is important to note here how these gates are woven together. By linking logic gates in various configurations, engineers create circuits capable of performing mathematical operations, storing information, and making decisions, all at speeds measured in billionths of a second. These logic circuits are connected by incredibly fine metal traces, which act as highways for electrons, ensuring that signals travel swiftly from one part of the chip to another. But the story does not end with two-dimensional patterns on a flat wafer. Modern microchips often employ three-dimensional stacking, a technique in which multiple layers of circuits are built atop one another. This vertical integration allows even more components to be squeezed into the same footprint, further boosting performance and efficiency. Nanotechnology also plays a role, enabling the manipulation of materials at the scale of individual atoms and molecules. These innovations are crucial as the industry pushes toward ever smaller nodes and greater functionality. The process of creating a microchip is not just a feat of engineering, but also of industrial choreography. Each step, deposition, photolithography, etching, and cleaning must be performed in ultra-clean environments where even a single speck of dust can ruin a chip. Wafers move through hundreds of machines, each performing a specialized task, monitored and controlled by sophisticated software. At the end of this journey, the wafer is tested and individual chips are cut free, assembled into protective packages, and readied for use in everything from computers and cars to medical devices and satellites. The drive to miniaturize and integrate more functions onto a single chip has led to remarkable advances in speed, power efficiency, and reliability. When millions of circuits are combined on one silicon platform, signals travel shorter distances, reducing the time it takes for information to move and cutting energy consumption. This integration also means that chips are less prone to failure since there are fewer external connections that might break or corrode over time. Even as the industry celebrates these achievements, the race to shrink features further grows ever more challenging. As the size of transistors approaches the width of a few dozen atoms, new physical effects emerge that complicate design and manufacturing. Researchers have responded with breakthroughs in materials science and manufacturing techniques. For instance, the use of advanced light beams and metal organic chemistry opens the door to even smaller and faster microchips, possibly heralding a new era in semiconductor technology. Despite these advances, there remain unanswered questions about how much further miniaturization can go. The industry continues to explore new architectures and materials, looking beyond silicon to alternatives that might overcome the current limits. Some of these emerging techniques, such as three-dimensional stacking and nanotechnology, promise to keep progress alive even as conventional scaling becomes more difficult. What is clear, however, is that the operational mechanics of microchips are the product of decades of relentless innovation. From the precise choreography of manufacturing to the microscopic intricacies of circuit design, every step is carefully tuned to coax the maximum performance from silicon. The result is a technology that has quietly transformed the world, making possible the devices and systems that define modern life. In the chapters that follow, we will look more closely at the frontiers of this technology, the new materials, techniques, and ideas that promise to drive the evolution of the microchip into the future. For now, it is enough to marvel at the ingenuity that allows billions of microscopic components to work together in perfect harmony, turning sand into the silicon souls that power our age. Imagine for a moment the invisible threads that weave together the fabric of daily life. A web spun not from silk, but from silicon. Microchips, those tiny marvels crafted from semiconductors, have quietly embedded themselves into nearly every aspect of the modern world. Their presence is almost ghostly, unseen, often unconsidered, yet absolutely essential. They are the silent animators of our devices, the unseen orchestrators of our routines, and the beating heart of technologies that have transformed how we live, work, and even heal. Think about your morning. The gentle buzz of your smartphone's alarm is powered by layers of microchips. One manages the operating system, another handles connections to Wi-Fi and cellular networks, and still others interpret your touch and adjust your screen's brightness. With a swipe, you check the weather, send a message, and perhaps tap an application to start your coffee maker brewing in the kitchen. Each step, each interaction, is a symphony conducted by microchips designed for specific tasks, working together in perfect harmony. Nowhere is the ubiquity of microchips more apparent than in consumer technology. Smartphones, tablets, and laptops are built around powerful processors and memory chips, miniature brains capable of executing billions of instructions per second. But the story goes deeper. Microchips also manage the cameras, regulate the battery, process sound, and enable wireless communication. Even unlocking your phone with a glance or a fingerprint is made possible by specialized chips designed for biometric recognition. Yet the reach of microchips extends far beyond the glowing screens we cradle in our palms. In telecommunications, they form the backbone of global connectivity. Every call, every video chat, and every search query races through networks of fiber optic cables and cell towers, all orchestrated by chips that route, encrypt, and decode streams of data in real time. These chips ensure that our voices and messages travel halfway around the world in the blink of an eye, weaving together families, businesses, and societies. At home, microchips have become the brains behind automation and convenience. Smart thermostats learn your habits and adjust the temperature with uncanny intuition, thanks to embedded sensors and logic circuits that process streams of environmental data. Security systems, doorbells, and lighting all respond to your voice or your presence, their intelligence residing in compact chips tucked away in plastic casings. The refrigerator that reminds you when you are low on milk, the speaker that answers your questions, even the washing machine that chooses the optimal wash cycle. All depend on the silent calculations of microchips. Nowhere is the transformative power of microchips more evident than on the open road. The modern automobile is a rolling testament to the microchip's influence. Far from being mere mechanical contraptions, today's cars are infused with a dazzling array of semiconductors, each tailored for a specific function. Safety systems rely on chips to monitor wheel speed, adjust braking force, deploy airbags with split-second timing, and even detect obstacles for automatic emergency maneuvers. Engine management units use microchips to optimize fuel injection and reduce emissions, while infotainment systems deliver navigation, entertainment, and connectivity, all coordinated by a network of chips communicating tirelessly behind the dashboard. The numbers are staggering. Recent analyses estimate that a typical new car contains thousands of individual microchips, each responsible for a distinct task, from controlling the cabin climate to adjusting the angle of the headlights. It is not uncommon for higher-end vehicles to be equipped with well over 100 separate electronic control units, all interconnected by high-speed data buses, a rolling network as complex as a small office building's information technology system. As vehicles have grown more sophisticated, so too has their reliance on microchips. Features such as adaptive cruise control, lane keeping, collision avoidance, and even autonomous driving are all made possible by specialized chips capable of interpreting sensor data and making real-time decisions. This dependence has not gone unnoticed. In recent years, disruptions in the global supply of microchips have rippled through the automotive industry, causing production lines to slow and buyers to wait months for new vehicles. Shortages of memory chips in particular have highlighted just how vital these components have become, not only in cars, but across smartphones, personal computers, and even the sprawling data centers that power artificial intelligence and cloud computing. Analysts are watching closely as demand for automotive and artificial intelligence chips continues to surge, suggesting that the humble microchip has become a linchpin of both mobility and the digital economy. The influence of microchips is equally profound in healthcare, where the boundary between science fiction and everyday reality is fading fast. Within implantable devices such as pacemakers and hearing aids, microchips regulate and monitor bodily functions, delivering therapy with exquisite precision. Modern medical diagnostics now rely on chips that can sense the faintest electrical signals or detect the presence of specific biomolecules, capabilities once reserved for the most advanced research laboratories. Tiny field effect transistor biosensors, for example, can read out biological information directly, opening new frontiers in point-of-care testing and personalized medicine. Innovations in drug delivery leverage microchips as well. Researchers have developed implantable systems that release medication in exact doses at precise times, tailored to the needs of each patient. These chips, barely larger than a grain of rice, can be programmed remotely or respond to biological signals, transforming the management of chronic diseases and improving outcomes. In hospitals, microchips are the foundation of imaging equipment and diagnostic machines, enabling the rapid analysis of blood samples, the reconstruction of detailed scans, and the real-time monitoring of vital signs. The precision, speed, and reliability of these devices depend on the relentless logic and processing power of their semiconductor cores. Microchips are also being used in ways that would have seemed like science fiction only a generation ago. Radiofrequency identification implants, for instance, can store personal and medical data just beneath the skin, allowing doctors to access critical information instantly in an emergency. While these technologies are still the subject of ongoing research and debate, they illustrate how the integration of microchips into healthcare is reshaping both what is possible and what is practical. The reach of microchips stretches well beyond the home, hospital, and highway. In agriculture, chips monitor soil moisture, track livestock, and optimize irrigation, helping farmers use resources more efficiently. In industrial automation, robotic arms assemble products with unwavering precision, guided by chips that interpret sensor data and issue commands in microseconds. Even in the farthest reaches of space, microchips power satellites and probes, perform autonomous navigation, and transmit streams of scientific data back to Earth. But with their ubiquity comes responsibility. The manufacture and use of microchips are not without environmental cost. The production process, requiring vast amounts of energy, water, and rare materials, generates significant carbon emissions and waste. As the world's appetite for microchips grows, so does the urgency to address these impacts. The industry is responding. Companies are investing in greener manufacturing processes, recycling initiatives, and more sustainable supply chains. Efforts are underway to reduce the carbon footprint of microchip production, from sourcing renewable energy to designing chips that are more energy efficient in use. Microchips themselves are becoming tools of sustainability. They enable renewable energy systems to operate more efficiently, regulate the flow of power in smart grids, and optimize the charging and operation of electric vehicles. In smart buildings and cities, networks of sensors and controllers, each powered by a microchip, adjust lighting, heating, and cooling to minimize waste. In transportation, chips help drive the shift toward cleaner, smarter vehicles and logistics. By enabling real-time monitoring and control, microchips are helping industries across the board become more resource efficient and environmentally conscious. Through all of this, the microchip remains the silent partner, small in size, vast in impact. It is present in the spark of a newborn's first heartbeat monitored in a neonatal ward, in the whir of a robotic harvester in a field, in the gentle hum of an electric car gliding down the road, and in the quiet click of a light turning on when you walk into a room. The microchip story is one of transformation, of possibilities unlocked and new worlds revealed. In the end, these tiny slivers of silicon are more than just components. They are the threads that bind together the technology of today and the promise of tomorrow. As we look toward the future of microchip technology, the sense of possibility is palpable. A blend of scientific ambition and practical challenge that promises to shape not only our devices, but the very fabric of society itself. The microchip, once a marvel of miniaturization and integration, now stands at the threshold of an era defined by entirely new architectures, materials, and ways of thinking. The next chapter in this story is already unfolding in laboratories and design studios around the world, where engineers and researchers are pushing the boundaries of what a chip can do and what it means for all of us. One of the most profound shifts on the horizon is the rise of quantum computing. Unlike traditional chips that manipulate ones and zeros, quantum chips harness the strange laws of quantum mechanics, allowing information to exist in multiple states simultaneously. This remarkable property, known as superposition, opens the door to calculations of staggering complexity problems in cryptography, chemistry, logistics, and medicine that would be impossible for even the most advanced classical computers to solve within any reasonable time frame. Recent breakthroughs have led to the development of chips specifically designed for quantum computing, featuring architectures that use exotic quantum states and materials. For example, some innovations focus on creating more scalable quantum chips, employing novel manufacturing techniques that allow stable quantum bits, or qubits, to be produced reliably in greater numbers. The implications are far-reaching. A quantum economy could emerge, reshaping industries and creating entirely new markets, while also forcing a rethinking of standards in areas like cybersecurity, where quantum algorithms could render current encryption methods obsolete. The dawn of quantum computing also brings new challenges. As quantum chips progress from laboratory prototypes to commercial viability, researchers face issues of scalability, error correction, and integrating quantum systems with existing semiconductor technologies. New chip architectures, such as those leveraging the Majorana particle, may offer pathways to more robust and practical quantum devices. However, even the most promising approaches must contend with the realities of manufacturing at scale and the need for specialized environments to preserve delicate quantum states. The global race to advance quantum technology is intense, with governments and corporations investing heavily to secure leadership in what many see as the next technological revolution. Alongside quantum advances is the meteoric rise of artificial intelligence in chip design. Creating, verifying, and optimizing a modern microchip is extraordinarily complex, involving billions of components and intricate interconnections. Traditionally, these tasks required years of work by large teams of engineers, but artificial intelligence-driven design tools are transforming the process. Today, deep learning algorithms and generative artificial intelligence systems automate large parts of the design workflow, from laying out circuits to debugging and verifying functionality. These artificial intelligence tools can identify potential errors earlier, suggest more efficient layouts, and model how chips will perform under various conditions. As a result, companies can bring new chips to market faster, reduce costly mistakes, and create designs that would have been beyond human capability alone. The impact of artificial intelligence on chip design extends beyond speed and efficiency. There is a growing trend toward using artificial intelligence to generate entirely new architectures, optimizing chips for specific tasks such as machine learning, graphics, or edge computing. Industry experts see this as a virtuous cycle. As chips become better at powering artificial intelligence applications, artificial intelligence in turn accelerates the pace of chip innovation. The semiconductor workforce is evolving as well, with engineers increasingly collaborating with artificial intelligence systems, focusing on higher-level problem-solving while routine tasks become more automated. This transformation brings its own challenges, demanding new skills, new educational pathways, and a reimagining of what it means to be a chip designer in the age of intelligent machines. Beyond quantum and artificial intelligence, several other frontiers beckon. Neuromorphic computing, for instance, seeks to build chips that mimic the structure and function of the human brain. These devices, still largely in the research phase, could enable more energy-efficient processing for complex tasks like pattern recognition and sensory integration. Nanotechnology continues to drive innovation at the smallest scales, aiming to pack even more functionality into ever smaller spaces. Three-dimensional stacking, where layers of circuitry are built atop one another, offers another route to increase performance and capacity, sidestepping some of the physical limits faced by traditional, planar chip designs. Yet the future of microchip technology is not only a story of technical possibilities, it is also a story of urgent global challenges. Chief among these is sustainability. The environmental impact of chip manufacturing has drawn increasing scrutiny, with concerns about resource consumption, chemical waste, and carbon emissions. Researchers and companies are responding with new methods for making chips that are less harmful to the planet. For example, water-based, environmentally friendly nanomanufacturing processes are being explored to replace hazardous chemicals and reduce energy use. Hybrid electronic biological devices, which blend conventional circuits with organic materials, may offer pathways to both improve performance and lower environmental impact. Sustainability is also becoming a core consideration in chip design itself. there is a growing emphasis on creating chips that consume less power, last longer, and are easier to recycle. Operational strategies for sustainability include efforts to reduce waste during manufacturing, source renewable energy for fabrication plants, and design products with their entire life cycle in mind. Looking ahead, these strategies are expected to become increasingly central, driven by both regulatory pressures and consumer demand for greener technology. As microchips become more complex and pervasive, the issue of security looms ever larger. The advent of quantum computing, for example, poses a unique threat to current cryptographic systems. Algorithms considered unbreakable today could, in theory, be deciphered by powerful quantum computers in the future. This has spurred intense interest in post-quantum cryptography, developing new methods of securing information that can withstand attacks from quantum-enabled adversaries. The transition to quantum-safe security standards will require not just new software, but potentially new generations of chips designed with these capabilities in mind. The economic and geopolitical stakes are also rising. The global race for supremacy in both quantum and classical semiconductor technologies has taken on renewed urgency, with countries and corporations vying for leadership. The transformative potential of quantum-enabled microchips is evident in projections of their impact on sectors as diverse as medicine, logistics, and national defense. As these chips move from laboratory curiosity to commercial product, they are expected to redefine industries and shift the balance of technological power worldwide. Of course, for all the excitement, it is important to acknowledge the uncertainties that remain. While the trajectory of progress in microchip technology is clear toward greater complexity, intelligence, and integration, the path is not without obstacles. Technical challenges in scaling quantum chips, integrating new materials, and ensuring the sustainability of manufacturing processes remain significant. Furthermore, the social and ethical questions posed by increasingly intelligent and autonomous systems powered by advanced microchips are only beginning to be explored. Despite these unknowns, one thing is certain: the microchip's journey is far from over. Each emerging trend, whether quantum computing, artificial intelligence-driven design, or sustainable manufacturing, adds a new layer to the unfolding story. The microchip, long a silent enabler of progress, now stands as both the tool and the terrain of our technological future. Whether in the form of chips that solve problems once deemed impossible, or circuits crafted with the health of the planet in mind, the innovations of today will seed the realities of tomorrow. As we close this exploration, it is tempting to imagine what the next generation might find commonplace: computers that harness the weirdness of quantum physics, devices that think and learn with the efficiency of the brain, and technologies that tread lightly on the earth. These visions are no longer the stuff of science fiction, but the logical extension of trends already underway. The future of microchip technology is being built now, layer by layer, idea by idea, a testament to human ingenuity and the enduring quest to make the invisible indispensable.